The tight still is designed to operate continuously for prolonged periods of time, and manual control requires frequent interventions to make measurements of temperature and hydrometer readings and power adjustments. Automated control offers better ease of use and precision. It depends on a closed feedback control loop where adjustments are made to boiler power to keep measured parameters of still function within specified ranges. Parameters to consider are product ABV, alcohol by volume, column top temperature, column temperature profile, and column bottom temperature. Column top temperature won't work, at least not as a sole parameter. You can see from this expanded bottom right corner of the water alcohol phase diagram that the difference in temperature between the top stages of an azeotropic distillation column is extremely small, thousandths of a degree centigrade. It varies with atmospheric pressure by much more than that, and any scheme to measure temperature so accurately is prone to errors that will also dwarf these small differences. Thermometric equipment that allows temperature resolutions down to a thousandth of a degree is extremely expensive, and for all these reasons column top temperature is not a useful control parameter. Product ABV is perhaps the most promising control parameter, but it's difficult to automate, especially if you're on a low budget with limited engineering skills and facilities. I have had some success with it. I tried two approaches. First was the Bob pycnometer parrot. This is my pycnometer bottle. It's useful for getting highly precise measurements of ABV, better than a precision hydrometer. It's a small glass bottle that's designed so that you can fill it to a fixed volume precisely and repeatedly. It differs from a volumetric flask in that the volume is not predefined. So, for example, this is a 10 ml pycnometer, but its actual volume is 13.542 ml. Every time it's refilled, it is the same 13.542 ml, whereas if it were a volumetric flask, its actual volume would be 10 ml. It's used for measuring relative density. You start by measuring the empty bottle on a milligram scale. Then you fill it with distilled water at a known temperature and weigh it again. Then fill it with your liquid of interest, in this case spirit, and weigh it again. You subtract the weight of the empty bottle from the second two measurements to get the weights of the same volume of spirit and water, and can so calculate the relative density of the spirit. And using the functions given in my plans below, you can derive its alcohol content from that density. Doing that, you can get results that are accurate to better than 0.01% ABV. That suggests rigging up a system with a parrot vessel of known volume whose weight is monitored electronically, but that proved to be impractical. The reverse was quite easy though, which was to rig up a parrot with a bob hanging in it from a load cell. The upthrust on the bob from the liquid around it is proportional to the liquid's density, and so the force measured on the load cell will be low with water and high with spirit, and from this measured force we can calculate spirit ABV easily and accurately. This works well on the laboratory bench, and I was easily able to measure alcohol content to an accuracy of better than 0.01%, but when I put it into a still, it went wrong for two reasons. First was that in the parrot, spirit flows up around the bob on its way from the column to the collection bottle, and this upflow has a somewhat random fashion depending on spirit drips from the column. That causes random fluctuations in the viscous drag on the bob, and this made its accuracy unacceptably poor. The other problem was drift. Cheap load cells, such as the one I use, can be very accurate, but unfortunately they drift significantly over time. If you take a cheap digital scales, every time you turn it on, it self-calibrates, and then you make a measurement within a few seconds, so drift is not important. But if you measure a force over many hours or days, it drifts by several percent, which is not acceptable. To get round the viscous drag problem, I put a solenoid valve that switches off the inlet to the parrot before a measurement is made. To get round the drift problem, I rigged up a system that lifted the weight of the bob off the load cell, allowing it to be zeroed before each measurement was made. That kind of arrangement is bread and butter to scientific instrument makers, but not so easy to pull off in a shed on a low budget. When I got it working, I was able to get high accuracy alcohol measurements. Advantages are that it is accurate. With a load cell and chip, you can easily cover the range of interest with 100,000 counts, giving a precision of better than 0.01% alcohol by volume. Also, it measures the parameter that we are most interested in. However, it also has disadvantages. It cannot be used as a sole control parameter. This diagram shows how several control parameters vary with boiler power. Below the optimal power, no product is produced, so you can't use its ABV to adjust the boiler setting. You have to develop a function with more than one measured parameter, adding a measurement of column temperature. A second disadvantage is that it's slow. In order to get high sensitivity with available load cells, I use quite a large bob, needing a large 35mm diameter parrot, which takes some time to fill with the still's low output. It takes a long time for changing alcohol concentrations to be reflected throughout the parrot. This can be improved by emptying the parrot after each measurement to avoid the slow mixing, but this adds further mechanical components. Thirdly, it's generally more difficult to implement a system with moving parts than one which is purely electronic, especially with limited budget and engineering facilities. The ones I made worked, but were fiddly and temperamental. The next approach I tried to using product ABV as a parameter was based on TDC GP22 chips, where TDC stands for Time to Digital Converter. These are designed to measure the flight time of sound waves through liquids flowing in pipes. The time taken for sound to travel between 2 points in a pipe depends on the speed and direction of flow within it. This allows flow rates to be calculated. They're used in a variety of industrial applications, particularly in heating systems, where heat flows are calculated from the temperature and speed of water movement. These chips are impressive. They can measure time differences with a precision of up to 12 picoseconds. As the speed of sound in spirit varies with its alcohol content, it's possible to make a parrot that works by measuring the speed of sound through a path of known length through static spirit. In principle, you could measure down to parts per million with a path length of only about 100 millimeters. These chips are cheap to buy and relatively easy to use. The problem is with piezoelectric transducers. You use one to make a click that travels through the liquid and another to detect the click, and the chip measures the time between the two. Cheap transducers just don't respond fast enough. For a practical parrot, the path length should not be more than about 10 centimeters, but to allow enough flight time to use cheap transducers would require a path length of a couple of meters. Superfast transducers are available, but they cost hundreds of dollars. So while I think this would be a good solution, I would leave its further development to those with better funding. The system I have used most is the temperature profile of the surface of the column. The lower few stages of the column run a lot hotter than the long isothermal section where azeotropic distillation occurs. We can use the length of the isothermal section as a parameter for controlling the still. The longer the better, but it needs to be at least 80 centimeters long. It does not need to be measured with high precision because the corner at the bottom of the isothermal section has a large temperature rise from 78 degrees to over 90 degrees over 3 or 4 stages. The aim is to set up a festoon of temperature sensors along the surface of the column and to derive the control parameters from the length of this isothermal section. If the bottom of the isothermal section gets too hot, power is reduced. Logically, that would mean that if it gets too cool, power is increased, but I have found that falling top temperatures is a better indication to increase power than is falling bottom temperature. In normal operation, the column is finely balanced just on the edge of producing no product. Starting with a column that's being overdriven with too much power, the isothermal section will be short and the product will have a lower ABV. As power is reduced, two things change. The ABV of the product rises and the length of the isothermal section increases. With progressive power reductions, the product ABV gets higher until it nudges over 96%. With further power reductions, the column stops producing any product at all and the column top temperature falls significantly. This top temperature change is more sensitive than bottom temperature change, which is why the control parameter is a function of both the column top temperature and the length of the isothermal section. You end up using just the top and bottom sensors of the isothermal section, so strictly you might think you don't need the others, but they are informative in the process of setting up and tuning the column, so I would keep them. The surface temperature sensor system is forgiving because it depends on temperature differences of several degrees rather than several millidegrees, but it's not perfect. For a 28mm copper column, I found that the column surface is 2 to 3 degrees cooler than the column core. This is close enough for the system to function, but with larger diameter columns that is no longer true. With wider columns, the difference between the core and surface temperatures gets larger, and surface temperature becomes a less reliable indicator of column thermodynamics. I have found that with a 35mm column, surface temperature measurement is marginal as a parameter and does not work as well as it does with a 28mm column. I give more details of this column temperature profile system in the plans linked below. When operating as a continuous still, there is an alternative temperature-based control method which uses the bottom temperature as the sole control parameter, rather than relying on a festoon of sensors up the column. With continuous distillation, the still gets a split between the product and bottom's ABV. If you increase the steam flow, the alcohol content of the bottoms will fall and its temperature will rise. Conversely, if you reduce the steam flow, the alcohol content of the bottoms will rise and its temperature fall. There is a predictable one-on-one relationship between this alcohol bottom's temperature and the operating conditions of the rest of the column. This parameter can be used to fix the alcohol ABV of the bottom of the column. That is the waste, and it's going to be around 0.1% alcohol by volume. This expanded view of the top left corner of the alcohol-water system phase diagram shows how the boiling point of the waste varies with alcohol content. It's only changing between maybe 0.05 and 0.15% ABV. The range of interest of the boiling point is a couple of tenths of a degree, so the temperature must be measured with greater precision and needs to be compensated for atmospheric pressure with a chip like the BMP280 on which I have made a video. Continuous distillation also adds in the need for digitally controlled precision pumps for feeding steam and wash into the still, and the whole continuous still project gets more technically challenging to get working. However, I have changed over to continuous distillation with a 35mm diameter column, where the column surface temperature system doesn't work well. I'm using this bottom temperature as the control parameter. It requires a specialized PID control system that cannot be implemented on cheap PID controllers like this. Instead, it has to be implemented on a small board computer. And additionally, the temperature has to be transformed with a mathematical function before applying PID control, all of which gives a lot of additional numerical parameters that have to be optimized. I haven't got it working as well as the surface temperature system with a 28mm column. I've got it to fairly reliably get over 95.5% ABV, but not over 96. I'll address it in more detail in a future video if anyone is interested. My next video will take up the matter of changing the column from a pot still into a continuous still.